Today, I will talk about the topology optimization and also combined with the topology optimization. How can deep learning can be utilized in the mechanical engineering, and specifically in this case is clinical applications. Before presenting my materials, let me briefly introduce myself again. I got all degrees from KAIST, and my research field can be categorized into two different fields: design optimization and multidisciplinary computational analysis. Here is background for today's talk. Human skeletal system consists of many bones, approximately 206. And today, I will focus on this, the proximal femur, which is one of the important long bones, which can support heavy self weight, and also it can provide a wide range of motions. In 19th century, many physicists and the anatomists and also the many researchers investigate, we have common features in proximal femurs. So according to Wolff's classification, we have the principal compressive groups and principal tensile group and secondary tensile and compressive groups. Interesting is, at the same time, the 19th centuries, the many engineers in the mechanical engineering revealed we have very strong analogies. If we focus on the crane-like the structures, we have very similar principal stress trajectory. So based on these interesting findings and observations, the well-known the German anatomists and also the engineers, the Julius Wolff, proposed the law of transformation of bone, which is also known as simply Wolff's law. This law simply states bone has self-optimizing capabilities and can control its mass and structure according to its mechanical demands. Based on this, many researchers revealed this phenomenon bone and bone remodeling. Actually, bone remodeling is a lifelong process where old bone tissues are removed. This is called simply bone resorption, and new bone tissues are formed, bone formations. In classical bone remodeling approaches, many researchers simplify these phenomena as in the form of simple time differential equations. Here, in these equations, if we have the higher the mechanical stimulus, so capital S is bigger than a certain reference value K, then we have increased mass. Conversely, if we have smaller stimulus, then bone density gradually decreases. If we have the same one, then we can say OK is in its own equilibrium. So by using these simplifications, as bone remodeling progress, the distribution of mechanical stimulus over the entire domain becomes gradually more uniform. So this phenomenon can be interpreted simply like this. If we have the target bone and if we have a specific surrounding mechanical condition, so definitely the hip joint contact force and muscle force in these cases, then under this mechanical boundary condition, we have bone remodeling induced by mechanical load. Then as a result, we have this very complicated structure. Trabecular bone inside the proximal femur. So we can say, okay, the surrounding boundary condition can be considered as cause, and the resultant trabecular structures can be considered as effect, cause and effect series. Then this same phenomenon can be interpreted in other aspects. Oh, sorry. If you view these same problems from the optimization viewpoint. Then causes can be considered as boundary conditions, and mechanical load-driven phenomena can be interpreted as sensitivities, and resultant, the structure, although very complicated, this is considered as optimal structure. In structural topology optimization, we first divide whole the design domain into a set of design domain finite element. Then each finite element has artificial relative densities. Here, if we have relative density 1, then that specific element is fully occupied. If we have simply 0, then this is simply air or other materials. Then, if we set the specific boundary condition, loading and geometric boundary condition, and then we set formula, the optimization formulation. So objective function in this case is compliance minimizations and constraint function, typically material or volume usages. Then, using sensitivity informations, then we can obtain the optimal material distribution like this. So in structural topology optimization, optimized structure becomes fully stressed or ideally evenly stressed under a given conditions. So if you compare the previous remodelings in biomechanics and this structural topology optimization, you can find very strong analogy between two seemingly different phenomena, bone remodeling and structural topology optimization. This is the research motivation. So based on this, the motivations, I started to reveal the secret between two things. So first test is the construct finite element model for proximal femurs using over 2 million the finite element. I constructed full proximal femurs, and then using initial random hollow surface, I made the initial structures for topology optimization. And also I considered 3 different loading cases, one extends abduction and adduction to represent daily activities. And here is the detailed optimization formulations. Here I use weighted summation of strain energy and bone mass. And also I put the parameter constraint here. But interesting is here I use this inverse directional inequality constraint because I'd like to obtain the higher parameter to conserve the velocity of trabecular structures. Then under this formulation, we can derive analytical sensitivities like this. Interesting is if we mathematically manipulate, then here the original sensitivity equation can be simplified like this. Then you can find that this is simple term for bone remodeling. So this can be considered as mechanical stimulus, and this next term can be considered as reference values. So again, mathematical viewpoint, we can find direct relationship between two different things. Again, this is the initial structures. Then under our settings, through some iterations, we can find these final structures. Then you can find if we have focus on 4 different regions of interest, then you can find we have totally different thickness and orientation and patterns for trabecular bone. This is because we have different surrounding the mechanical conditions for each region of interest. Then another interesting is again, we have common features for proximal femurs. Again, principal compressed group to support hip joint contact force, and we have principal tensile group as a bending cantilever beam, and secondary tensile, secondary compressed group. Interesting is here, we have same features in the final topology optimization result. Then I compare this numerical result with actual the patterns. I got the photograph image for the cross-section of the proximal femur. We can find a very strong analogy between two things. And then for saying the specimens, I took the plane radiograph image. Although this is the inverse the images, but we can find very similar triangular patterns. So I successfully obtained very complicated structural patterns for our scatter system. Then my next goal is, what is the useful items to use these interesting features? So I move on to the next topics. In clinics, we used DEXA to assess our bone health. So you may have seen this kind of the imaging devices. And when we use this one, then we can measure the average bone mineral densities for these given the areas. Using this information, we can measure whether it is the health or not. But unfortunately, because we only use the area average bone mineral densities, it can account for bone strength with 60 to 75% variation. So it can cause misdiagnosis or overdiagnosis. We can solve this problem if we have the detailed microstructure for proximal femur. Then the assessed bone strength assessment can predict up to 94% of actual bone strength. But the problem is, in clinical practice, we have only the limited resolution, about the 600 micrometer when we took the CT. Then we have decimal between these two. We require higher resolution, 50 to 100 micrometer. Then how can we solve this one? Actually, in terms of medical imaging, we use CT or MRI in clinical practice. Again, it provides around the 600 micrometer resolutions. But micro-CT and HRPQ-CT can provide around 50 micrometer resolution. But problem is, as the resolution increases, we have excessive radiation exposure and excessive scanning time. So we cannot use these two in clinical practice. So our goal is to provide the new schemes. So if we have a certain product optimization-based scheme, then if we have low resolution the medical image, then we can reconstruct very fine bone structures. Then using this bone structure, we can do something like the finite element structure to assess bone strength. Then using this quantitative information, we can provide more reliable diagnosis. This is our goal. Then to approach this goal, we made this flowchart. Then actually it consists of three important steps: pre-processing, localization, and resolution enhancement. First, pre-processing. When we have the low CT scan images, then it actually contains many garbage information. Then through automatic segmentation, which we developed, then we can obtain the full segmented femurs. Then this can be converted into relative density map for proximal femur. This is required to conduct topology optimization. Second step is localizations. When we have only 600 micrometer, then we have 0.45 billion. So this is acceptable. But if we consider 10 times upscaling to acquire 60 micrometer, then actually it leads to 0.45 billion. So it is practically unaffordable. So how can we solve this problem? Our solution is localization. You know the matrix, the partitionings or substructuring in finite element structure. If we handle this full proximal femur, then we can make three different regions: global regions and local regions for volume of interest, and cut boundary between two different regions. Then we can construct this partitioned matrix. Then when we solve these full models, then we can obtain the displacement field for cut boundary. Then using these informations, we can obtain the local load for the volume of interest. So we can obtain both spatial density distribution from the CT scan data. This is measurable data. And second one is we can approximate the local load on the cut boundary of local models. Then it means we are ready to solve the topology optimization. Here, objective function is compliance minimization. Second one is BMD derivation from CT scan data. Then this is actually very simple. Here, left one is the measured data, and second one is we have the additional 1,000 degree of freedom for the given original boxes. But for these sub-boxes, average value should be the same of the measured data. So we impose this constraint for each original boxes. So this is the meaning of the constraint function. And then iteratively conducting this one. Then we need to validate the proposed method. So for this purpose, we acquired microcity images for 6-4-year-old Korean males. In these cases, the resolution is 78 micrometers. And then after acquiring this microstructure, we intentionally downscaled 8 times. Then this can be used as the low resolution input values. And then when we apply our proposed method, then we can obtain the result. Then that result can be compared with the reference values. Okay, again, we have reference values, and using that, we have the low resolution input data. Then using conventional interpolation-based scheme, cubic and unclosed, we have very blurry image. But when we use our proposed topology optimization-based method, then we have very clear image. But we need to quantitatively analyze this result. So for this purpose, we use automatic indexes, which are frequently used in the field: conversion fractions, average particle thickness, and spacing, like that. In terms of these quantitative measures, our reconstructed image have maximum 3.8% errors compared with the reference image. This is quite amazing, and it means we obtain morphologically very meaningful result. And third variation is bone strength. Actually, bone strength is the most important measure in this field. So we measure 3 directional bone strengths: anterior, posterior, medial, lateral, and superior, inferior. This means backward fall, side fall, and normal standing during daily life activities. And here, again, this is reference image, and for this one, we can measure bone strengths. And in this case, we measure the stiffnesses. But interesting is that when we use low resolution input image, it provides quite high errors, maximum over the 300%. So when we use these values, it can cause misdiagnosis and overdiagnosis. when you use interpolation-based scheme, it also have very unacceptable higher errors. But interesting is when you use our method, then it provides maximum 5%. So based on this quantitative result, we can conclude we obtain structure very close to the structures. Then, what's the problem of this approach? To reconstruct simply only 1 cubic centimeter trajectory, it took average the sense 15 to 35 hours. It means it's meaningful, useless in clinical practice. Then how is it possible to enhance this clinical image in real time? So we started to use deep learning. Again, topology optimization is explicit program, but deep learning is opposite, different approaches. Then, to obtain good models, we need well-designed and well-trained artificial neural network. Then, what's the problem in the specific field? If we have low resolution scan data and we don't like to obtain high resolution enhancement, then typically we use image to image, right? But in these cases, the target images too complicated, very, very complicated, many velocities. And another problem is we have lack of training data because we cannot use microcity for the living persons. This is the problem. So our solution is to reflect on remodeling phenomena. We don't like to use structural information guided or physics informed neural net. And also we can generate input data by using topology optimization. So we don't like to link between cause and effect. So we slightly modified our strategies. So by using the combined topology optimization and deep neural networks, we'd like to reconstruct bone microstructure within a shorter time frame without significant loss of accuracy. For this purpose, we generated training data again using topology optimization, which I already explained. Here we use a total 11 images, and for these small domains, we constructed training data. The total number of training data is 120,000. Yes, and then we selected the CNN. In this case, this figure shows UNet CNNs. Then the difference is we inserted one additional layers to include structural behavior. In this case, it's displacement field and strain energies. Then feed forward and that propagation, we trained the CNNs, and we use MAE or the other ones. I will show you again. So through this tedious process, we successfully enhance low resolution image to the high resolution. Interesting is when you compare the reference images, it seems good, right? And also compared with the original topology optimization, it took 1 hour, but in these cases, it took much less than 1 second, right? So, it's good. And then this is only patchwise reconstruction. So we use this image quilting algorithm. This is very simple. Between two patches, we made intentionally overlap the regions, and then we measured error maps. And then by using dissector algorithm, we can make the most smooth cross sections between two regions. Then using that, we can fit 2 different patches. So by using these fitting algorithms, this is the reference obtained from topology optimization. Then after obtaining all the patches, then by using fitting algorithm, we constructed this one. Again, this is really big images. So very big, large scale 2D images, but it seems very, very similar, right? But if we focus on the specific reason, then there is the notable difference between 2. But another problem is, if we measure the apparent stiffness, then it provides around the 50% errors, regardless of the different one, ResNet and the UNet, the SI GAN, something like that. The main problem is here. When we obtain the reconstructed images through the deep learning, we have this kind of many local disconnectivity, artificial local disconnectivity. So this causes the significant error in bone strength. So again, it seems feasible, but we have still far to go. Let me conclude this talk. Human skeletal system is naturally designed from the viewpoint of optimization. So this is amazing and interesting. So topology optimization and deep learning can be useful tool for the patient-specific diagnosis. So I will do the more focus on the deep learning augmented resolution enhancement. Thank you very much for your attention.